Okay, thank you. All right, good morning, everyone. My name is Yixin Chen, and this is work with my student Roying and my colleague Wei Xiong. So today I'll talk about a set-based approach to optimal temporally expressive planning, and then I will talk about a new temporally expressive planning domain motivated by P2P Network Optimization. So in this problem, there's a lot of concurrency that needs to be exploited. And finally, I talk about some results. So yesterday, we were already seeing a couple of talks on temporally expressive. So I think we are pretty familiar with the background. So temporally expressive problems are those that require concurrency. So basically, two actions needs to be executed in parallel in any valid plan. So for example, if there are two actions, 1 and 2, if action 1 requires a precondition F, and only action 2 provides that precondition at the beginning and would delete that fact F at the end of action 2, then of course action 1 and action 2 has to be executed concurrently. So this is one reason why the concurrency is required. And also, for example, if you have deadline, and in order to catch the deadline, you have to make concurrent plans. So some facts about temporally expressive planning. So many existing temporal planners are not really temporally expressive. And also, most planning benchmarks, those used in the recent international planning competitions, are also not temporally expressive. Namely, you can find plans, the actions have durations, but you don't require any of them to be concurrent. So these are temporally simple problems. But required concurrencies are obviously very important in the real world. Many problems we can imagine, they do require concurrency. So for example, the P2P network problem I'm going to introduce today, to serve a lot of files, you do need to upload and download files at the same time. So concurrency is very important. So there are some existing temporally expressive planners. This list is not most up to date. There are more recent works. So these are just some examples. So for example, state space search, there are Crikey 2 and Crikey 3, some other variants, and there are partial order based planners and some other planners. So in this paper, we introduced a set-based approach to temporally expressive planning. So the idea is very simple. So basically, it follows the set plan framework. So we encode a planning problem as a set problem. But in this encoding, we would be able to handle the temporally expressive features, and we allow concurrent actions. So in our model, we have discrete time, so we cannot handle continuous time. Our solution will be optimal in terms of the overall time span or the overall duration of the plan. And in order to transform the original temporal planning problem into set, we first need to model a durative action as a pair of simple actions. So basically, for each action, if it's temporal, then we would introduce two actions. One represents the beginning of that action, and the other one represents the ending of that action. And also, we introduce a new fact to represent that, to indicate that the action is being executing. And then we can transform the problem after we introduce the simple actions into a set encoding. And then we just solve a sequence of set instances. So starting from a small time step, and then we increase the time step until we find a solution. But each time we can increase the time step by a delta that can be user defined. For example, we can use delta is 5 or delta be 10. But to guarantee optimality, so we actually used an idea proposed by Ray and Ginsberg in 2008 that we modify the DPLL algorithm in set solving. So in set solving, for each time step, we introduce a variable to indicate that the goal is going to be satisfied. All the goals are satisfied at that time step. So, but during set solving, we would enforce some orderings of the variables. So we would first set the earliest goal variable to be true. We always try that first. Set that variable to be 1. If that fails, then we will try the next one. So in that way, we can guarantee optimality. So some details about our set encoding. We define the action variables and factor variables. These are standard for each time step t. For each action, each fact, we introduce a variable. And there are a bunch of goal set variables. So for multiple time steps, for each time step, we define a goal variable. So during the branching in the set solving, we would try to enforce some ordering between those goal variables in order to achieve optimality. And there are a bunch of clauses. These are all standard clauses that used in set plan, including initial state, the goal state, precondition, add effects, and delete effects. And also for durative action, so the first clause represents, basically says that if the action begins at time step t, then the action will end at time t plus rho minus 1, where rho is the duration of that action. And also, if an action is executed at time step t, then for the whole entire duration of that action, FO is true, where FO means the action is being executed. And then also all the preconditions that needs to be satisfied during the action would be true. So there are 3 types of preconditions. Preconditions that has to be satisfied at the beginning, preconditions that has to be satisfied during the action, and preconditions that has to be satisfied at the end of the action. So here, this notation means the duration of the action. And also we can handle axioms. So for each axiom, we add some clauses. So when the preconditions of an action is satisfied, then all the effects are also true at that time step. And finally, we have the mutual exclusion constraints for the actions and facts. So that's our encoding. So and that's the first part of my talk. So basically, I introduced a encoding, set encoding for temporally expressive planning. Nothing special, just a very simple translation. And then we modify, because really there's not many, there's very few temporally expressive domains. We have seen the match lift domain introduced yesterday. So here we introduce a new temporally expressive domain based on P2P Network Optimization. So we all have, I guess most of us has watched the movies or videos online that based on P2P network. That's very fast, and but the reason it's very fast is because they have a lot of concurrency. So basically, each computer can upload and download files at the same time. So for each file, we can have multiple copies spread it out at those computers, and you can download files from multiple sources. So, but there are topology constraints, file availability constraints, and upload and download speed constraints. So obviously, there's a large room for improvement of the overall network throughput. So we represent this problem in PDDL 2.1 after making some simplifying assumptions. So currently, the model, I would say, cannot really be immediately used for industry, but it does capture the essence of P2P network optimization, and we can potentially extend it to real-world application. So our goal is to optimize the overall time to get all the peers' data delivered. So this is a metric that is in the middle ground of 2 extremes. Because from the user's viewpoint, a user would want to download his file immediately as quickly as possible. But in that case, it will maybe sacrifice the time of other users. From a network provider's point of view, they want to minimize the total network traffic. They do not like P2P networks. In our case, we just minimize the overall time. That means we optimize the overall network throughput. We have a number of constraints. So to download a file, a computer must be routed to a serving computer that has a copy of that file, and also that computer is serving the file. Because uploading is typically much slower than downloading, so we specify that each computer can serve at most one file at any time. So if a computer has different files, but at each time they can only provide one file. So therefore, you want to really exploit concurrency, because when the computer is serving a file, you want multiple computers to download that file. We try different, we randomly generate different topologies of the network. In each problem instance, we have files with different sizes. Therefore, they take different time to download. And then initially, each computer may have its own collection of files. And the goal is that each computer may want some files from other computers. So this problem really requires a lot of concurrency, like I said, because when a computer is serving a file, you really want to, you can download a file only when a computer is serving. So therefore, concurrency is really required. And also, in order to maximize the throughput, you want to you want multiple computers to download the same file at the same time. Of course, subject to like network topology constraints. So to provide a little bit more insights into the characteristics of different domains, we defined a notion called temporal dependency. So basically, an action is temporally dependent on another action if the action has a precondition that is provided by the other action at the beginning and will be deleted at the end of that action. Okay? And we plot some domains. For example, the trucks domain, there's no temporal dependency. In the match left domain, so we can see that, so each arrow represents a dependency. So we can see that there are lots of dependency, but it's not everywhere. So there are still lots of actions that are not temporally dependent on any other action. But in the P2P domain, we can see that almost all the actions are either temporally dependent or being dependent by some other actions. So therefore, this domain is more requires more concurrency. So here are our results. Basically, we compared with two versions of Crikey. So this is on the original match left domain. So the STEP is our solver. So it stands for Set-Based Temporally Expressive Planning. And we give the overall time and the quality. The quality is the total duration. So we can see that the time took much longer, but the quality is much better. Right? In this table, we can see the trade-off. So normally, Crikey 2 or 3 cannot find the optimal solution, and sometimes it's almost twice as longer as the optimal plan our planner can find. But on the other hand, our planner is much slower. Right? But if you look at the number of matches, so in the second column, we have 4 numbers, L, M, R, U. M, the second number is the number of matches. And U is the number of fuses that needs to be fixed by the electrician. So we can see that it's always the case that M equals to U. That means you have the same number of matches and same number of fuses. Therefore, for each match, when you lift it, you only need to fix one fuse. So there's low degree of concurrency. So that's our modified domain. So because we have a generator of this match lift domain, so we modified so that if you look at the second column, the number of matches now is fewer than the number of fuses. All right? So therefore, when you light a match, you need to fix more fuses, right? It cannot just fix one fuse, right? So you need to exploit more dependency. And in this case, we can see that steps can outperform the crack key. So, for example, in the highlighted problems, it's both faster and also provides better quality, right? And also for the for problems from number 7 to 12, crack key 2 and 3 would fail cannot find a solution in a time limit of I believe it's 1 hour. Cannot find any solution, but we can find a solution. And also, if you look at number 12, it's very interesting because in number 12, there's only one match and there are 8 fuses. So therefore, you have to optimally utilize that match. So therefore, you have to generate very concurrent domains, very concurrent plans to finish the task. So that is very difficult, so crack key cannot find the solution. But the step solve the problem in only 3 seconds and find the optimal plan. So the reason is for set solving, when there are a lot of concurrency, so basically it provides very strong constraint through unit propagation. So therefore, actually the space becomes so constrained that you can prune a lot of infeasible regions very fast during the set solving and find a solution very quickly. But if you look at number 11, well, we have 3 matches. It's an easier problem, but steps will take half an hour to find a solution because they are not so strong constraints. So it needs to explore very deep in the tree. And this is on the P2P network optimization problem. Again, because we see that the problem is a lot of concurrency, so we see that crack key 2 and 3 perform not as good as step. And there are some domains where we are faster and also get better quality. And also, if number 1 to 6 are actually easy problems because there are less files, and also each node will connect to at most 2 other nodes. So there's low degree of concurrency. But number 7 to 12 are actually very difficult problems because there are a lot of files, and almost every computer will require all the other files from all the other computers. So it's a lot of concurrency. And finally, this last domain is called drivers log shift. This domain is difficult for our planner because it has very long durative actions. So we have to extend it one by one, so it's very expensive for steps. So if we compare steps against crack key, we find that our planner is much slower. But our quality, of course, because we are optimal, is better. And crack key 2 actually has a little flaw that, because if you look at the quality of crack key 2, it's pretty good. It's almost always optimal. But it has some plans like that where the driver has to rest and drive at the same time. So, but crack key 3 definitely fixed that problem. So, in conclusion, we feel that both search-based and set-based planners are very a good approach, but they are suitable for different kind of domains. I think search-based planner is more suitable for problem with a lower degree of required concurrency, but set-based planner is suitable for problem with high degree of concurrency, but the action duration is not too long. So there's a trade-off there, and so it depends on the domain. So that's it. Thank you very much. So I'm sorry, I don't quite understand your questions.
Okay, so how you produce is, so it's because it's not trying to minimize an external point.
Right.
So if something like a matter of saying it will bend or fuse,
right.
then bend another,
right.
then bend another,
right.
even though that could be done parallel. You can find that parallel is post-hoc by doing partial logarithm, which was in trying to 2 but not trying to 3, which is why often why it has better plans.
Okay.
So you have to look at trying to 3 to actually see if plans do have that structure to see actually
Oh, I haven't looked at that, but I think it's a very good suggestion. Yeah.
So, am I correct in thinking that step does not do metric?
That's correct. Yeah. It's difficult to model metrics in set model at this time. Yeah.
Hi. I wanted to understand more about your required concurrency, the whole issue here. So it's clear to me that concurrency is important to optimize, but as far as peer-to-peer networks, it seemed like there was the strictly required concurrency was due to your encoding and not the domain. Like if you re-encoded it so you had mention a link, link these two computers, then it's not strictly required.
You're saying remove, merge, download, and upload to one action that's called link. All right. Yeah. So there are at least two sources for concurrency. One is you have to download and serve at the same time. That can resolve this issue. But again, to minimize the time, so you have to several links have to execute together. But because one file can be one computer can serve one file at each time. So when the computer is providing this file, you want to be linked to multiple computers at the same time.
Right. So I'm just saying that's an optimization goal, not necessarily that doesn't follow the original definition of required concurrency doesn't talk about optimization. So.
Yeah, I agree that the encoding does affect, right? If does affect to a certain degree. But for example, I could add a deadline to this domain. Then I could say in any valid plan you require concurrency. So it depends on how you see it. But